So basically, in this question, there are two characters, Alice and Bob, which are playing a game on an integer array of size n. Game is like this that the array is initially colorless, and Alice can choose three elements and color them red. Now Bob comes and chooses any elements and color it blue. Alice wins if the sum of the red element is strictly greater than the sum of the blue element. Basically, Bob gets to choose one element and he can choose whatever element, even if it is colored red or if it is colorless, he can choose the element, and the sum of the remaining element should be strictly greater than the chosen blue element if Alice should win. So our task is to calculate such elements whether our task is to calculate the number of ways in which Alice can choose three elements in order to win. So let's look at the input before just proceeding towards the solution. Just look at the input. Here we can see that constraint is very less, like it is 5000 only. So we can run a solution close to n square or n square log n type of. We can run such solutions n square log n. Since constraint is very low, n square will be 10 raised to 6, which is possible to run in 2.5 seconds. And also we can see that the array is already sorted. So these are two observations that we can make. Now, greedily, let's suppose if we were Bob, then greedily we will always choose, or let's suppose we were Bob, then greedily we will always choose the largest element since we know the array is already sorted. So greedily we will choose the largest one. That is something we will always do. So let's say I choose three indexes I, J, and K. Given the point that A of I is less than A of J and A of K less than equal to A of K. So let's suppose I have chosen three elements. Then the sum of chosen one A of I plus A of J plus A of K should be strictly greater than A of N because Bob can choose that. But Bob can also do one more thing. Bob can also either he can pick the largest element of the array or he can pick the largest element that we have chosen. Bob can just do these things like Bob can choose any element from k to n. Also, uh, Bob can or Bob will pick any elements from k to n. So we have to make sure that we have to make sure that a of I plus a of j is larger than a of k as well. Since Bob can choose this and Bob can also choose this, so we have to make sure that this is clarified. So solution requirements is really simple. There is nothing really complex about it. We can just as we discussed earlier, that solution can have n square log n complexity. So we can just pick a for loop from 0 to n minus 3, and then just we can just pick another for loop from I plus 1 to n minus 2, and inside here we can just apply a binary search. What we have to do in the binary search, let's discuss that in detail. So let's suppose this is the index line j plus 1. From the elements after j are obviously greater than j plus 1. So we can just simply do one thing. We can find last index. We can find last index that obeys this point, that obeys our second requirement. A of I plus A of j is greater than A of k. We can just find this thing. We can find this thing. So let's say if the last index that obeys this, it's s. So we will be having something like this: j plus 1 to s. So from j plus 1 to s, all the element obeys this point. Then we have to check for the first point that we had chosen. That was a of I plus a of j plus a of k. Sum should be greater than a of n, strictly greater than a of n. So we can just find first such point that this condition is applied. Also, we can just rewrite it as this: last element such that we can also rewrite the same condition as this one. We can find an index that last element such that the sum is less than or equal to a of n. If we find such element to be ss, then we can just simply do ss plus 1. So we will be sure of the fact that ss plus 1 to s are all our solutions. Okay, so we can simply find s minus ss plus 1. We can just simply do s minus ss. Let's say s is the last index where this thing happens. Then we can just find s minus s to be our answer. We can just include it. For the given I and j, s minus s indexes will satisfy this thing. Will satisfy the required condition, condition 1 and 2, that the sum of the element is larger than a of n and the sum of the smaller 2 is greater than the larger one. So we can just check, we can just do this thing. Let's look at the code. So here we can see I have taken input ll of n, bl of array, and just taken the input and then start answer with value 0, and then just as I said 0 to n minus 3, and then I plus 1 to n minus 2, and then just I have applied this version of this particular variant of binary search, where what I am doing is first I am ensuring the second condition, that is I plus j is greater than the mid one, and then I am ensuring after finding the last index, last s, such that the condition is satisfied, I am finding ss. Ss is what? Ss is nothing else but ss is the last index such that the value is lesser than or equal to n. Sum of all three is lesser than or equal to n. Ss is the last such index, and then just we do answer plus s minus ss. One thing that can come to your mind is that why we are checking for the second condition first, then the first condition. Why we are not doing first and then second? This is because I want to make sure that a of I plus a of j is greater than a of k, because my k can be anything from j plus 1 to n. So I just want to make sure that my a of I and j are already larger than a of n, even if the chosen elements are I, j, and n. So this is the very reason why I am doing this before the whole question. Why I am doing the second step before the first. This is the very reason. So I think the explanation is enough for this one. Let's move forward to the next problem. So the second problem is shrinking array. What it tells us that there is a array which is beautiful if it consists at least two elements. So there are minimum two elements in the array, and there is exist a position I such that bi minus bi plus 1 is less than or equal to 1. So the absolute difference between the I and I plus 1 is less than or equal to 1. Okay, so we can do, okay, we are given with some operations. Let's look to them. We can choose any index I and I plus 1 and replace them. Replace AI and AI plus 1 with X. Okay, so we can just erase this A of I and A of I plus 1, and with any number X. X has to be between a of I and a of I plus 1. Minimum of a of I plus 1, and maximum of x has to be between them. Okay, so this is all. So we are asked to calculate the minimum number of operations required to make the array beautiful, or report that it is impossible. So, and the constraints are like n is also 1000. This is also pretty noticeable. Also, we have to report minus 1 if it is not possible, or if it is possible, then we have to report the minimum number of operations needed. So, let's discuss about different scenarios that can happen. First scenario would be there, if I had to talk of some scenario, then the easiest scenario will be there that no operations are needed. No operations are needed. So ऐसा सिचुएशन कब होगा जब ऑपरेशंस की नीड ही नहीं होगी. तो ऐसा सिचुएशन तब होगा जब देयर इज ऑलरेडी एग्जिस्टिंग एन एलिमेंट आई and an element at some index I, such that the absolute difference between a of I and a of I plus 1 is less than or equal to 1. So we can just first check this thing manually, and if there is such index, then we can just return answer as 0. This is something where we don't have to do any operations. Now let's just talk about the second situations, which can be impossible. When is this impossible? That is also important. Let's say if the array is increasing, means it's sorted, increasing like this, or like this, or it is decreasing like this, or like this, or like this, means array is in the sorted format. Let's take an example and see. 1 3 5, or better if I keep the example like this: 1 3 and 5. You can see, no matter how hard I try, if I choose my I to be I, if I choose my I to be 0 at the 0th index, then no matter what I do, I can always have a pick from 1 to 3 inclusive. There will be no element available to me such that the difference with the 5 is going to be less than or equal to 1. Let's suppose if I had further elements like also, we are sure about the fact that we have checked this thing before. No operations we have already checked. Then we are coming to this state. So whatever elements we have are obviously not at the not at some difference less than or equal to 1. So let's suppose we have 7, 5 or 7. So let's say if my I is now 1, if I choose 1 to be my I, then also no matter how hard I try, I can pick no element between 3 and 5 such that its diff with 7 is less than or equal to 1. Because I can pick, because I have already seen that the largest I had was 5, and it has a diff of 2 with, it had a diff of 2 with the 7. So no matter what you choose from 3 to 5, the difference is always going to be larger than already existing difference. The same scenario happens with descendingly sorted array, or reverse sorted array, whatever you call it. The same scenario happens. Let's say you keep it like this: 7, 5, 3, and 1. 7, 5, 3, and 1. This is 1. The same scenario will happen if I have I as 0. Then I can already see that the largest diff over here is between 5 and 3 is 2. So no matter what I choose from 7 to 5, I will never have a number which has a difference lesser than 2. So I am never going to make the array beautiful by just applying operation over here. I can also not do this by applying over here, by applying at 5, by applying at 3. I just can't do that. It's just impossible. So in the cases where array is sorted, the answer is -1. This is something we are very clear of. Now let's move forward to the minimum or the minimum thing. Now let's just move forward to the minimum operations required. See, we are going in a cycle like this. First, we check whether no operations is required. If the condition is like this, that there are no such I key index is there are no such i's that difference is less than or equal to one, then we move forward to check for impossible condition. For impossible condition, we are checking whether the array is sorted or not. If the array is not sorted, then we can check for the minimum operation condition. Now, what we will do in minimum operation? First thing that we are going to get is the array is unsorted. Unsorted means it has peaks or crest. The array is something like this. It can also be like this. It is always going to look like this. Now, if you notice, the peaks or crest can be like this or can be like this. Okay. So okay, this is lesser than this point. Let's say for some I, this is the scenario in a unsorted array. For some I, this is the scenario. It is above this I minus 1 means the value over here is larger than this I minus 1, and I is the largest element. And here, as you can see, it is lesser than both of them. And here we have I minus 1 is again, I minus 1 is again the second smallest, and then I plus 1 is the largest. Or we can also have such scenario where I is the largest, I minus 1 is the second largest, or I plus 1 is the smallest. Or we can have such scenarios as well. I minus 1 is the largest, I is the smallest, and I plus 1 is the second smallest. In either of the case, there can be these four cases, and in either of the case of having these peaks or crest, we can clearly see one thing, that is, let's say I have a crest like this, I have a peak like this. So this element happens to be the smallest, then this element happens to be smaller than this 3, and then there is this element. So we can see that in whatever side of this the smallest and largest reside, जहाँ पे भी सबसे छोटा और सबसे बड़ा वाला एलिमेंट है, जिस भी साइड पे जो सबसे छोटा और सबसे बड़ा वाला एलिमेंट होगा, उनमें हमें ये वाला एलिमेंट ज़रूर मिल जाएगा. कहने का मतलब ये है कि जहाँ पे भी सबसे छोटा और सबसे बड़ा एलिमेंट है, उनके बीच में हमेशा ये थर्ड, ये वाला एलिमेंट है ना, जो मिडिल एलिमेंट है, वो हमेशा एग्जिस्ट करेगा. यू कैन जस्ट create any example and see this thing. Let's suppose if I reverse this thing and I have this 3, 5 and 1. यहाँ पे देख रहे हो, इस ये वाली साइड हमारी सबसे छोटी है. So 1 to 5 के बीच में तुम्हें 3 मिल जाएगा, जो मिडिल एलिमेंट है. तो तुम्हें मिडिल एलिमेंट हमेशा छोटी वाली साइड पे मिल जाएगा. ऐसी साइड जो सबसे लार्जेस्ट और सबसे स्मॉलेस्ट को कंटेन करती है, उसमें तुम उसके बीच में तुम्हें हमेशा पॉसिबल होगा इसको ले पाना. Let's say 1, okay, this is the largest, 5, and then smallest 1, and then 3. We will always be able to find 3 over this. So for any set of element, say a of I plus 1, and then a of I, and then a of I minus 1, हमेशा जो साइड ऐसी होगी जो स्मॉलेस्ट और लार्जेस्ट को कंटेन कर रही होगी, उसके बीच में तुम्हें मिडिल मिल जाना सबसे ज़्यादा ईजी होगा. This is something. So यहाँ पे we can simply see that we just have to do one operation, because अगर अरे तुम्हारी अनसॉर्टेड हो गई तो तुम्हें और ऐसे इंडेक्स मिल गए जो पीक या क्रेस्ट हैं. पीक या क्रेस्ट समझ में आता ही है. तो ऐसे एलिमेंट्स मिल गए जो पीक या क्रेस्ट फॉर्म कर रहे हैं, then the minimum operation required is going to be 1 only. Since 1 क्यों होगा? इसलिए होगा चाहे पीक का केस हो या क्रेस्ट का केस हो, हर एक केस में तुम्हारे पास जो ऐसी साइड होगी जो स्मॉलेस्ट और लार्जेस्ट को होल्ड कर रही होगी, वो हमेशा इस मिडिल एलिमेंट को भी इसके मतलब इसका मिडिल एलिमेंट इसके बीच में ही होगा, ये 1 और 5 होगा और ये 3 ही होगा। तुम कोई भी सिनेरियो क्रिएट करके देख लो, तुम्हें हमेशा यही चीज़ मिलेगी कि जो लार्जेस्ट और स्मॉलेस्ट कंटेन करने वाला साइड है पीक और क्रेस्ट का, वो हमेशा ये जो मिडिल एलिमेंट है इसको मतलब वो इसके बीच में ही लाई कर रहा होगा। तो हम लोग 1 और 5 को जस्ट रिप्लेस कर सकते हैं 3 से, एंड देन वी हैव 3 3 एज गिविंग डिफरेंस लेस देन और इक्वल टू 0। So for unsorted case, this is the thing. For code part, we can just simply show it like this. First here, you can say we are taking input and doing everything else, initializing answer with 1, 0, and then just we can check for this thing that the minimum operations required are 0 or not. If there is, okay, so the minimum operations is required or not. If it is not required, then it's totally fine. Then we can just move forward and give answer as 0. If it is required, then what we can do is simply just check for this crest and tuff thing. If we find a single crest or tuff in our array, means the array is unsorted, then the answer is 1. Simply, if there is even a single crest or tuff, so in this implemented solution what I am exactly doing is I'm taking an index I, and I'm just checking whether it is I'm just like you can see over here, I am picking an index I, and I'm just making sure that if it is sorted or not. If it is sorted, then I'm doing nothing. Means if the if it goes like this, I'm doing nothing. But if it is like this for 3 elements, then that means answer is 1. But if it goes like this for all i's, that means it is sorted simply. You can also implement it in a simple way. This first you can check whether there is already existing element such that there is already existing I such that I comma I plus 1 is giving you difference less than or equal to 1. Then also it is totally fine. And then you can just check for the sorting, and if you don't find it to be sorted, then you can just give answer as 1. But if it is sorted, then you can give answer as -1. What I am doing over here is I am just checking for any index I. I am just checking if it is like this. I am just checking this small point, or I is less than or equal to. Either it in sorted or uh, ascendingly sorted or descendingly sorted. I am just checking this thing, and if it is neither, then answer is 1. Why? Because if it is neither, then this or this is there. Either a crest or trough is there. I hope the examples were easy to understand, right, and easy to implement. The questions were not too hard. Now let's move forward to the last problem. So we have this question as a race. So basically what it asks you to do is Alice and Bob participate in a game TV show, and there will be prizes dropped to a certain point. Whoever gets to the prize first wins the prize. Means whoever reaches to the prize first, he or she wins the prize. So Alice has already decided her starting point. So Alice has already chosen some point A to be her starting point. That is fine. Then Bob, however, has not chosen any starting point. But Bob knows that the prize will be dropped at either at the point X or at the point Y. He also knows that he can. Okay, if Bob can reach the prize with a distance by traveling a distance less than less, then he wins it simply. And what is defined as the distance is just the modulo of, so just the difference of this both the points. If there are two such points C and D, then the distance between is nothing else but the absolute difference between them. That is simple. So you have to determine whether Bob can choose an integer that would guarantee his victory. So in this question, we have to first make sure that we are given 2 points X and Y, and price can be dropped to any of these. Means we have to find such a point for Bob that no matter what point Bob is present at, he can pick the price in lesser time than ls. So price can be dropped to x and y. If the price is dropped at x and Bob is at some point p, then also you have to reach faster than what time it will take for a. If the price is dropped at y, then and Bob is at some point p, then also you have to reach faster than a. This is something we have to make sure. So we have to win the race in both the cases in order to make sure that the Bob always wins. So let's say, let's make some cases where the a will be. Let's say, okay, before starting the problem, I am also ensuring this point that I am making this thing that I am making uh, x to store the maximum of x to store the minimum of x and y. I'm just doing this thing to make the thing easier, and y to store the maximum of x and y. I'm just making this thing. You can just check if it is not matching, then you can just simply, if you can simply sort it, swap it if this thing is not there. If it is already there, then just leave as it is. Now we have point x and y on the coordinate axis. Let's discuss about some cases where our a can be here, a can be here, or a can be here. So there are three feasible cases that can be mainly divided into two parts. What are the two parts? X okay, our a can be either here or here, or our a can be here, in between, somewhere here. So let's discuss the first case first. If x and y, if our Bob is here at this point, if a is here, then can we see that Bob can always choose some point in this range, including x, and its distance will be always lesser than what distance a would take to reach x and y. For example, if 4 comma 5 are x and y and our a is 1, then we can choose any number from 1 to 4, including 4, such that since we are not restricted to not to choose x and y, we can choose anything except a. We can choose any number from 2 to 4, and its distance will always be lesser than what the distance it will take a will take. So we can always choose any point a plus 1. So answer in such cases where a is simply lesser than x, okay, answer is always yes. Let's discuss in the very similar fashion. We can say for x and y, if a is somewhere here, then also we can choose any point from a minus 1 to y, and its distance from a will always be lesser, okay. We can choose any point, and its distance for x and y as compared to a will always be lesser. So answer here also will be yes. That is pretty trivial. I don't think it really needs any explanation. Let's suppose if it is 1, 4 and 5, our a is a, our a is 5 and y is 4 and this is x. Then if the we can always choose 4 to be our point. Then for if the price is at y only, then the distance traveled would be 0. If price is at 1, then the distance traveled would be 3 for Bob. And for ls, for here it will be 1, which is obviously larger than this. So in this case Bob wins. And for here 1, it will be 4. Here also it is larger than the Bob's travel distance. So here also Bob wins. So as we see, Bob wins both. So there is no such issue. And in such situations also, Bob answer is yes. So we have concluded that answer is yes for both of these situations. X less than or equal to x, or if a is greater than or equal to y. Also, what we can see is now there is the second condition left. That is हमारा जो बॉब है, हमारा जो पॉइंट ए है, एलिस ने जो चूज किया है, दैट इज इन बिटवीन देम. If it is in between them, then let's take an example and try to understand what is going on. Let's suppose if it is 1, comma 5 and the chosen point is 2. If this is the story, then we can see that no, the options available to us will be all points of x, all points of x and y, all points including x and y, except a. We can choose all such points except a. But as we can see that, let's suppose if I go on choosing some point over here. Let's say if I go on choosing 3, then for 3 the distance will over here will be lesser, but for 5 the distance will be lesser for 3, but for 1 the distance would be greater than what 2 will take, what a will take. So for all conditions that exist, we can say that no matter what point we choose in between, if distance for 1 specifically is lesser, let's suppose if I choose some point over here and distance for this point p for x is lesser than what distance a will take, then it is obvious that the distance that a will take to reach y is obviously lesser than what p will take. So p is not going to win this case. But if I do the reversal, like if I choose our p to be closer to, let's say if I choose our p to be closer to y, then also we can see that if p is closer to y, then our the distance a would take is larger than this, so a definitely doesn't win this. But the distance p will take to travel to x is obviously going to be larger than what a will take to travel to x. So in this case a wins. So we are not winning both the cases. There can a thought there can a thought that come into your mind. There can be a thought that comes into your mind, that is x and y, and we choose the middle point. That really doesn't matter if we choose the middle point. If a is not choosing the middle point, if a is present over here, then definitely the distance that a will take to travel to y is obviously going to be lesser than what we are going to take. The same story lies over here. So we can just conclude this point that if a is between, we can simply make conclusions like this. If a is between x and y, then answer is no. If our a is between x and y, then answer is definitely a big no. So you can just code this simple thing. There is nothing really complex in this. We can just look at the implementation. What I did was this. I calculated. Okay, this thing is not really required. You can just simply remove it. And just checking for the fact that if a is either greater than both of them or if a is lesser than both of them, in either of the case we win. That is it. So this is simply some version of this thing. So I'm assuming the answer initially to be no, and then just I'm checking this thing. My a is if my a is either here for x and y, or if my a is here. I'm just checking this thing by this code that you can see if either a is larger than both of them or a is smaller than both of them. In that case, the answer would be yes. So it was